Ever wondered how a packet leaving your laptop actually finds its way across thousands of independent networks to reach a server on the other side of the planet? Welcome to Lesson 31 of our networking journey, BGP Fundamentals. This is where we step out of the comfort of a single organization's network and into the protocol that ties the entire internet together, the Border Gateway Protocol, the language autonomous systems use to talk to each other. Before we dive in, let's map out where we're heading. We'll start by understanding autonomous systems, the fundamental building blocks of internet routing. Then we'll explore why BGP is called a path vector protocol, meaning it carries entire routes rather than just distance metrics. From there, we'll contrast eBGP and iBGP, same protocol, but very different rules of engagement. And finally, we'll unpack BGP's attributes and the path selection process that decides which route actually wins. So let's start with the foundation, the autonomous system, or AS. Think of an AS as a network, or a group of networks, all run by one organization under a single routing policy. The internet itself is roughly 75,000 of these ASs, all peering and exchanging routes with each other. Each one gets a unique AS number. Cloudflare is 13335, Google is 15169, Anthropic is 12618, and the range from 64.512 to 65.534 is reserved for private use, so you can experiment in your lab without stepping on anyone's toes globally. Now, how do all those autonomous systems actually talk to each other? Through BGP, the Border Gateway Protocol, the one and only language spoken between ISPs on the global internet. It runs over TCP port 179 for reliability. It's a path vector protocol, and peering relationships are configured manually because deciding who you exchange routes with is a business decision, not something you want happening automatically. And here's the key insight that trips up everyone coming from OSPF or EIGRP. BGP doesn't pick the fastest path. It picks the path that matches business policy, who you pay, who pays you, and who you have contracts with. Now, here's where BGP gets interesting. It actually wears two different hats depending on where you're peering. When you peer between two different autonomous systems, that's eBGP, external BGP, with an administrative distance of 20 and a default TTL of 1 because your neighbor should be directly connected. But when you peer inside the same AS, say R1 to R2 within AS 65,000, that's iBGP, internal BGP, with an AD of 200 and multi-hop behavior by default. And the critical rule to remember, iBGP never re-advertises routes learned from another iBGP peer. That's why, as we'll see later, you need a full mesh or route reflectors inside your AS. So how does BGP actually make decisions and avoid loops? Through something called a path vector. And the star of the show is the asPath attribute. Every route carries a running list of every autonomous system it has passed through. Watch how it evolves. As 100 originates 1010/16 with an empty path because it owns the network. As 200 hears it and prepends itself, so the path becomes 100. By the time it reaches as 400, the path reads 300 do 100 100, a complete breadcrumb trail back to the origin. And here's the elegant part. If any router ever sees its own AS number already in that list, it simply rejects the route. Loop prevention built right into the protocol. But before any of those AS paths get exchanged, two BGP speakers have to actually become neighbors, and that happens through a 6-step state machine. It starts at idle, just waiting for a trigger, then moves to connect as TCP reaches out to port 179. If that handshake fails, you land in active, which confusingly is the problem state, not the healthy one. From there, open sent and open confirm exchange parameters and keep alives, and finally established. That's when update messages start flowing. And here's the troubleshooting gold. Where a session gets stuck tells you exactly what's broken. Stuck at idle? Check your config. Stuck at active. TCP problem, stuck at open sent. Your ASN or authentication doesn't match. Once the session is established and updates start flowing, every route arrives decorated with attributes, and these are the knobs you turn to shape policy. The well-known ones are mandatory, as path for loop prevention and path length. Next hop, telling you where to forward, and origin, showing how the route was learned. Then come the policy levers, local pref, to choose your preferred exit out of your S, med, to hint to a neighbor which entry point you'd prefer, community tags for flexible matching, and on Cisco gear, wait, purely local, never advertised. Remember these names because the entire best path decision we're about to walk through is just BGP evaluating them in order. Here's the actual decision tree. BG walks for every prefix, top to bottom, and the first step that breaks the tie wins. Wait comes first, but only on Cisco and stays local. Then local pref for your AS-wide exit policy. Then a preference for routes you originated yourself. Then the famous shortest AS path, which is where most real-world decisions actually land. After that, origin, med, eBGP over iBGP, IGP cost to the next hop, and finally, oldest path or lowest router ID as deterministic tiebreakers. The mnemonic at the bottom, we love oranges as oranges mean pure refreshment, is worth memorizing. It'll save you in an exam and on a 2 a.m. troubleshooting call. Now let's actually configure it. 4 lines get you a working eBGP session. Enable the BGP process with your own ASN. Set a router ID so logs and troubleshooting make sense. Define the neighbor with its IP and remote AS and advertise your network. And remember, that network statement must match a route in your table exactly, or BGP silently refuses to announce it. Then, show IP BGP summary is your truth. When you see established with a prefix count, you're peering. Anything else, idle, active, open, sent, means you've got work to do. And speaking of work to do, let's talk about the traps that catch even experienced engineers. That exact match rule I just mentioned, it's pitfall number 1. Fix it with a null asuro static route or use redistribution. Then there's iBGP, which doesn't advertise routes between peers, so you need a full mesh, route reflectors or confederations. Watch your next hop too. eBGP learned routes keep the external peer as next hop, so your internal routers can't reach it unless you configure next hop self. Forget AS path filtering, and you might accidentally become a transit AS for 2 ISPs. And if your eBGP peer isn't directly connected, remember the default TTL is 1. You'll need eBGP multi-hop. So let's tie it all together. An autonomous system is a network under one administrative control with one routing policy identified by its ASN. BGP itself is a path vector protocol running over TCP port 179, using AS path to prevent loops, eBGP between ASs, iBGP within one. Attributes like wait, local pref, AS path, and med drive every decision, and the selection order is what you should commit to memory. Wait, then local pref, locally originated, shortest AS path, med, eBGP over iBGP, and finally IGP cost. Master that latter, and you understand how the internet chooses its paths. Here's your reference card for everything we covered. Keep it close. The essentials are right there. BGP 4 from RFC 4271, path vector over TCP 179, administrative distances of 20 for eBGP and 200 for iBGP, the public and private ASN ranges, and the core attributes that shape decisions. And don't forget the simplest loop prevention trick in networking. If a router sees its own AS in the AS path, it just drops the route. And that wraps up our deep dive into BGP. Next up in Lesson 32, we're shifting gears to redistribution and route maps, how you share routes between different protocols, and just as importantly, how you filter and shape them along the way. If BGP taught us how autonomous systems talk to each other, redistribution is how your internal protocols learn to cooperate. I'll see you in the next one.